Welcome back. I hope you enjoyed those little video clips from young Frankenstein. Frankenstein! At any rate, what was going on there? What was going on is that all humans have sort of a default setting of thyroxine. And for most of us, we have a normal level and our metabolic reactions are at a normal rate. But Marty Feldman had a case of hyperthyroidism. That means he had an overactive thyroid gland and he always maintained higher than normal levels of thyroxine. So these eyes that you saw on Marty Feldman when he was playing Igor, all right, this was not due to makeup. This was his natural condition, these bulging eyeballs. This was part of one of the symptoms of his hyperthyroidism. And for him, it worked out well for him. He was quite successful as an actor, and Young Frankenstein was just one of his works. Now, the opposite condition is called hypothyroidism. And in this condition, a person has an underactive thyroid. And here we're going to look at a gentleman. This is him in his untreated condition. He has lower than normal levels of thyroxine. So his metabolism rate is low. He's not very effective at breaking down glucose. Therefore, he's not very effective at burning up calories, releasing the stored energy of glucose. So this is him in untreated form, and then he was given thyroxine, and lo and behold, he had a normal body shape. All right. Up there's some more more pictures of Marty. I just like Marty Feldman. What can I say? All right. So to summarize, let's talk about some of the anterior pituitary hormones that we've mentioned. All right, TSH is thyroid stimulating hormone. As we've already gone over, it's released by the anterior pituitary and its target tissue is the thyroid gland. There's FSH, which we'll talk about in the next module, and it is a gonadotropin, which means it goes to the gonads. LH is another gonadotropin. So a pituitary is a pituitary is a pituitary. Both men and women have an anterior pituitary. The anterior pituitary of both men and women release both FSH and LH, but in men, FSH and LH affect the testes, and in women, FSH and LH affect the ovaries. All right, another anterior pituitary hormone is ACTH, and this affects the adrenal cortex. And so what ACTH stands for, as you can see, is the adrenocorticotropic hormone. Yes, that's a mouthful. You can see why we just call it ACTH. All right, there are even more hormones released by the anterior pituitary. There's growth hormone. I'm sure you've heard of this. If you have an underactive pituitary and you don't release enough growth hormone, you could be what's called a pituitary dwarf. You will not grow as tall as you normally should. So growth hormone affects the liver, it influences bone growth, and it also increases blood glucose level. And prolactin is yet another anterior pituitary hormone, and in mammals, it's responsible for milk production. All right, one word that we haven't fully defined is the word tropic hormone. A tropic hormone is a hormone that controls other endocrine glands. So why don't you look at the anterior pituitary and think to yourself, which of these are tropic hormones? Which influence other endocrine glands? Well, it should be pretty obvious. TSH affects the thyroid gland, so that's a tropic hormone. The gonadotropins, they go to the gonads. That's why they're called gonadotropic hormones. They control the gonads, so these are tropic hormones. And ACTH, this goes to the adrenal cortex and it causes it to produce cortisol. So these are all clearly tropic hormones. So you see again why the anterior pituitary is called the master gland, because it secretes many hormones that control other endocrine glands. So as a little example of this, let's say you're stressed. This stimulates the hypothalamus to release its releasing hormones. Again, this is the capillary connection between the hypothalamus and the anterior pituitary. The pink here represents the releasing hormones. They go to the anterior pituitary and stimulate it to release ACTH, right, adrenocorticotropic hormone, which circulates all throughout the bloodstream, but the target cells are in the adrenal cortex. So remember, the adrenal cortex is the outer part of the adrenal gland. The medulla is a totally different gland in the middle. And as I said before, the adrenal medulla, when it's stimulated, it secretes adrenaline. But the adrenal cortex, when it's stimulated, it secretes the hormone, the steroid hormone, I should add, cortisol, which helps you deal with stress. A little interesting experiment scientists once did. They removed the adrenal cortex gland from some rats, and they stressed it daily, and this is all they did to stress it. They submitted it to loud noises. They submitted the rat to loud noises repeatedly. They didn't hurt it physically. They didn't starve it. All they did is, with regularity, expose these rats repeatedly to a periodic loud noise. Yeah, you get the idea. You would not believe what happened to these rats. They dropped dead due to stress. Yeah. So we'll learn about this in a second. This is sort of a negative feedback system. So stress is what initiated this whole hormonal pathway. The hypothalamus stimulates the anterior pituitary. The anterior pituitary releases its hormone, which stimulates the adrenal cortex. The adrenal cortex secretes cortisol, and the cortisol is a hormone which allows us to deal with stress. So yeah, these rats just dropped dead because they could not deal with stress. Interesting, huh? So if you're in college, you need your adrenal cortex glands. All right, I'm going to change my little pointer here. You are not going to have to know all this information. All right, just to summarize, that the master gland is really two glands. You don't need to know all this. Just to review, the pituitary is really two different glands. The anterior and posterior pituitary are made of two different types of tissues. You don't need to know this. They secrete two different types of hormones. And as I have emphasized, they have two different connections, ways of communicating with the brain or the hypothalamus. All right, we have focused on the anterior pituitary. Now we're going to look at the posterior pituitary. So as I've already mentioned, that there are your brain cells are called neurons, and there are these neurosecretory cells that secrete the posterior pituitary hormones. So the hormones of the posterior pituitary are actually made in the hypothalamus. These little globulars roll down here, and they are actually stored in the posterior pituitary. And when the hypothalamus says when, these posterior pituitary hormones are released into the bloodstream. And the two hormones released by the posterior pituitary are vasopressin, which is also known as ADH. I'll show you how to spell that on the next slide, and oxytocin. And this is showing you the target of both vasopressin and oxytocin. The target of vasopressin are the kidney tubules, and the target of oxytocin are the mammary glands and the uterine muscles. So to review, the two hormones secreted by, or at least stored in and secreted by, the posterior pituitary are oxytocin and vasopressin. Now, vasopressin is also known as ADH, which stands for anti-diuretic hormone. So a diuretic is something that makes you urinate more often. So anti-diuretic hormone would imply that it makes you urinate less, which is actually exactly what it does. ADH, it causes you to pee less. So another way to say that is vasopressin or ADH regulates your urine output. And again, this hormone part of the course has been minimized, and so I'm going to focus on oxytocin, which, as you observed in the last slide, this affects the mammary. The target tissue is the mammary glands and the uterine muscles. But just to review, what's true about both oxytocin and vasopressin, they are made in the hypothalamus. We've covered that. The little droplets travel down the neurons, the neurosecretory neurons, down to the posterior pituitary. They're stored in the posterior pituitary until it's time for them to be released into the bloodstream. All right, so oxytocins, they stimulate the mammary gland cells to release milk. That's one of their actions. And the other action, which is related, is it causes the uterine muscles to contract. So Maybe you learned in health class there's three basic types of muscles. There's smooth muscle, which is involuntary. There is cardiac muscle, and there's striated or voluntary muscle. So if you've ever known a woman who has had a baby, she will tell you that her uterine muscles are not voluntary. They are not under voluntary control. Trust me. If you're in uterine labor, that uterus just contracts, and you have absolutely no control over it. Well, what's going on is oxytocin is what causes the uterus to contract. Now, before we talk about childbirth, we are going to talk about that other role of oxytocin in milk production. And this is important because this is an example of a positive feedback loop as opposed to the negative feedback loop we saw before. So this is what happens. When you have a nursing baby, the baby starts to suckle at the woman's breast. The suckling is the stimulus. Now, this might not come as a big shock, may or may not come as a big shock to you, but a woman's breast has a neuronal connection with her brain. So her brain senses when her breast is being stimulated, when it's being suckled. Her brain, specifically the hypothalamus, stimulates the posterior pituitary to release oxytocin. The oxytocin has target cells in the breast tissue, and that causes the milk, which has already been made, to be released, and the baby has access to it. So when the baby gets the milk from the breast, he thinks, hey, this suckling works. I'm getting my food. So what the baby does is it suckles even some more. Again, you have the electrical impulse, goes to the hypothalamus. The hypothalamus causes a release of more oxytocin, more milk is released, and the baby continues to suckle. So again, remember, in a negative feedback loop, the original stimulus was diminished or even reversed. In a positive feedback loop, the original stimulus is reinforced. So the child suckles, he's rewarded with milk, that causes him to suckle more, he's rewarded with milk. So here's a little diagram of that. So here's the original stimulus, the suckling. It causes the release of oxytocin, which causes the release of milk, which causes the child to suckle more, and so on and so on and so forth. So how does this stop? How does this feedback loop stop? Well, you know the answer. The kid gets full. So there's an interruption in the cycle. The kid stops suckling, no more oxytocin is released, no more milk is released. Got it? Well, if you understand that, you should understand the next one. I forgot to, I wanted to say one more thing about nursing. So oxytocin is released in nursing. Now, it might surprise you that oxytocin is released in both males and females, and it's also known as a trust hormone. And this makes sense in nursing. Oxytocin is one of the mothering hormones. When a woman nurses her baby, oxytocin helps her feel these feelings of love and connection with her child. But like I said, it's also called the trust hormone. It is released in both males and females during the sexual response, which again is a good thing. You should trust the person that you're having sexual intercourse with. All right, back to positive feedback loops. A positive feedback loop involving oxytocin often also happens during labor. All right, imagine a woman, we'll go into this more when we talk about reproduction. You have a baby in a uterus. Do you know what the bottom of the uterus is called? The bottom of the uterus is called the cervix. So usually a baby is born head first, so the head is pressing against the bottom of the uterus. All right, so I don't know, this would be a really bad picture here. So we have the bottom of the uterus and we have the baby's head trying to get out. There's the baby's head. Terrible drawing. Here's the baby's. Terrible drawing, arms and legs and stuff. All right, as the baby's head pushes on the bottom of the uterus, the cervix, all right, again, these nerves send an impulse to the brain, all right, which causes the hypothalamus to release more oxytocin. Well, what does the oxytocin do? It causes the uterus to contract. As this uterus contracts, the kid is pressed down, the kid's head is pressed on down on the cervix even more. As there's more pressure on the cervix, more electrical impulse, the nervous impulse goes to the brain, the hypothalamus releases more oxytocin, there's more uterine contraction, the head keeps pushing on the surface, cervix, and so this goes on and on and on and on into what? What breaks this positive feedback loop? the kid is born. Once the kid is born, the head is no longer pressing on the cervix, and there's no more oxytocin released and no more uterine contractions. In fact, I have to tell you this personally. I was always amazed in these childbirth videos where this woman looks like she's in total pain, and then as soon as the kid pops out, she was all happy. And I thought, there is no way that's true. If you start pounding your thumb with a hammer and then stop, that thumb is still going to hurt. Well, guess what? Those movies are right. As soon as the kid pops out, you feel great. All right, we're going to end up with one more Dr. House moment. Dr. House wants to know if you understand the positive feedback loops involved with nursing and labor and oxytocin, how could you use this information to facilitate the delivery of twins? In fact, if you can figure it out, you will have figured out an age-old trick learned by midwives. So enter your comments in the comment box and we'll let you know the answer later. Hope you've enjoyed this presentation. Goodbye.